It might sound crazy, but it's true. We're living in an ice age right now. I know it's hard to believe, especially on a warm day. But this ice age actually started about 2.6 million years ago, and technically, it hasn't ended. The really wild thing is that every 100,000 years, like clockwork, our planet goes through these insane transformations. Massive ice sheets spread across huge parts of the continents, and then they melt away again. So, in this video, I want to break down this 100,000-year cycle. I want to understand how it works, why it happens, and the kind of world it creates during these cold phases. I want to show you the creatures that thrived in Ice Age conditions and how humans managed to survive and adapt. And, perhaps most importantly, I want to explore why it all seemed to come crashing down so recently. We'll even touch on where we are in the cycle right now and what that might mean for our future. Let's start with the basics. An ice age isn't just a cold period. It's an extended chunk of time. We're talking millions of years, where Earth's temperature drops enough that massive ice sheets and glaciers take over large portions of the planet's surface. We're currently in the Pleistocene Ice Age, which kicked off about 2.6 million years ago and technically hasn't ended yet. Now, within any ice age, you get fluctuations. There are glacial periods where it's really frozen and interglacial periods where it warms up. We're in an interglacial period right now and have been for about 11,700 years. So, when people say the Ice Age, they usually mean the last glacial period, which lasted from about 115,000 years ago to 11,700 years ago. That's when the ice sheets were at their biggest and the megafauna were running the show. During that last glacial period, the temperature was only about 6 degrees Celsius colder than today, on average. 6 degrees doesn't sound like much, right? But we're not talking about 6 degrees in one spot. We're talking about 6 degrees worth of thermal energy being sucked out of the entire planet. All the oceans, all the land masses, the whole atmosphere. That's enough to completely transform the world. Huge ice sheets covered most of Canada and northern Europe. The Laurentide ice sheet in North America and the Fennoscandian ice sheet in Europe were kilometers thick in some places, because so much water was locked up in ice. Sea levels dropped by over 100 meters. You could walk from England to France. You could stroll from Asia to Alaska, across what's now the Bering Strait. The coastlines were completely different, and the landscape was mostly tundra and cold grasslands, dry and windswept, nothing like the forests we see today. So, what caused this? Why does Earth go through these dramatic swings every 100,000 years? The answer, surprisingly, starts with a Serbian scientist named Milankovitch. Back in the early 1900s, this guy figured out something nobody else had really considered. What if ice ages weren't caused by anything happening on Earth, but by changes in Earth's position relative to the Sun? See, Earth's orbit isn't perfectly circular. It's slightly elliptical, and the shape of that ellipse changes over time because of gravitational pulls from other planets, mainly Jupiter and Saturn. Sometimes our orbit is more circular, sometimes it's more stretched out. And this cycle of changing from circular to elliptical and back takes about 100,000 years. That's the first Milankovitch cycle, called eccentricity. When Earth's orbit is highly elliptical, the distance between Earth and the Sun varies more dramatically throughout the year. This affects how much solar radiation hits different parts of the planet at different times. And here's the crucial part. It's not about how much total sunlight Earth gets. It's about where and when that sunlight hits. Northern Hemisphere summers are the key because that's where most of the land is. If Northern Hemisphere summers are cool enough that winter snow doesn't fully melt, the snow sticks around. Year after year, it piles up. Eventually, you've got ice sheets forming. And once ice sheets start growing, they reflect more sunlight back into space, which cools things down even more, which allows more ice to form. It's a runaway feedback loop. But eccentricity isn't the only cycle. There's also obliquity, which is the tilt of Earth's axis. The more tilted Earth is, the more extreme the seasons. This tilt varies on a roughly 41,000 years cycle. When Earth is less tilted, the difference between summer and winter is milder, which means summer might not be warm enough to melt all the winter ice. Ice accumulates, and an ice age begins. The third cycle is precession, or wobble. Earth wobbles on its axis like a spinning top. It's strange to think that the Earth's climate is, in some ways, like a spinning top that's slowly starting to wobble. This wobble, known as precession, changes which hemisphere tilted toward the sun at different points in our orbit. It's a cycle that unfolds over about 26,000 years, and it affects the contrast between our seasons. Right now, the northern hemisphere experiences winter when Earth is closest to the sun, which makes our winters milder than they could be. But that wasn't always the case, and it won't always be. When we combine the effects of eccentricity, obliquity, and precession, we find that they work together to control Earth's long-term climate patterns. What's truly baffling is that the 100,000-year eccentricity cycle, the cycle related to the shape of Earth's orbit, is actually the weakest of the three in terms of its impact on incoming solar radiation. Logically, the other two cycles should matter more. But when scientists began extracting cores from ocean sediments and ice sheets to reconstruct past climates, they discovered that the dominant pattern was, in fact, the 100,000-year cycle. It's as if the weakest player somehow dominates the entire system. This puzzle is known as the 100,000-year problem, and scientists are still working to fully explain it. The leading theory suggests that there are feedback mechanisms at play that amplify the eccentricity cycle. Perhaps it takes a very long time for ice sheets to build up, but they can collapse relatively quickly. This means the system spends most of its time slowly accumulating ice during the cooler phases, only to melt rapidly when conditions shift towards warming. This asymmetry could explain why the 100,000-year pattern is so prominent. What we do know for certain is that for the past million years or so, Earth has been cycling through these 100,000-year climate shifts. Slow ice buildup over tens of thousands of years, followed by relatively rapid melting, and then the cycle begins again. During those cold phases, the world became a stage for some of the most incredible animals ever to walk the planet, the megafauna. And the word mega is no exaggeration. Some of these creatures weighed 4,500 kilograms or more. There are theories about why everything grew so large during ice ages. One idea is Bergmann's rule, which states that in colder climates, mammals tend to be larger. A larger body has a lower surface area to volume ratio, meaning less heat loss. So, bigger bodies stay warmer more efficiently in the cold. That's why polar bears are bigger than other bear species, and why Ice Age mammals tended toward the gigantic. But size alone doesn't tell the whole story. These animals possessed incredible adaptations for surviving in a frozen world. And the most famous example, the poster child of the Ice Age, is the woolly mammoth. Woolly mammoths weren't actually as huge as you might think. They were about the same size as modern elephants, maybe a bit shorter, but their bodies were structured completely differently. They had thick, shaggy fur with 2 layers, a dense underwool, and longer outer guard hairs. This coat could be up to a meter long in places, providing insulation so effective that mammoths could endure temperatures of 40 degrees or colder. They also had small ears to minimize heat loss, unlike modern elephants, with their big, floppy ears used for cooling off. And they had a layer of fat up to 9 centimeters thick for extra insulation and energy storage. Their skulls were specially shaped, too, with large sinus cavities that helped warm and humidify the cold, dry air before it reached their lungs. Breathing in super cold air can damage your lungs, so this was a crucial adaptation. And their teeth were perfectly suited for grinding the tough grasses and sedges that grew on the mammoth steppe, a unique cold grassland ecosystem that covered huge areas during glacial periods. As their teeth wore down, new ones would move forward from the back of the jaw. A mammoth would go through 6 sets of teeth in its lifetime. We know so much about mammoths because some have been found frozen in permafrost, almost perfectly preserved with fur, skin, and even stomach contents intact. Scientists have studied what they ate, extracted their DNA, and found that they had special hemoglobin variants that worked better in the cold, allowing their blood to deliver oxygen more efficiently in freezing temperatures. These animals were fine-tuned for Ice Age conditions. But mammoths weren't alone. The Ice Age world teemed with megafauna. Woolly rhinoceroses roamed the same landscapes, covered in thick fur with massive horns that could reach over a meter long. They used these horns to plow through snow to reach the vegetation underneath. Giant ground sloths lived in the Americas, and these weren't the cute little tree sloths we know today. Some species weighed several tons and could stand up to 4 meters tall on their hind legs. They were too big to climb trees, so they lived on the ground, feeding on vegetation and, incredibly, digging burrows. We found their burrows, tunnels up to 40 meters long with claw marks on the walls that match their fossilized claws perfectly. There were glyptodonts, basically car-sized armadillos with shells made of fused bone plates. They couldn't roll up like modern armadillos, but they didn't need to. Their shells were tough enough to stop most predators, and some species had club-like tails covered in bony spikes that they could swing as weapons. Recent studies suggest they might have been able to rear up on their hind legs, which means you could have had these armored tanks standing upright and swinging spiked clubs. That's both awesome and terrifying. And then there were the predators. Saber-toothed cats prowled the Americas with canine teeth up to 18 centimeters long, curved like daggers. They used these to deliver killing bites to the throat or belly of prey, causing massive bleeding. Cave lions in Europe and Asia were larger than modern lions. giant short-faced bears in North America might have been the largest mammalian land predators ever, standing over 3 meters tall on their hind legs. Dire wolves hunted in packs and had more powerful jaws. I've always been fascinated by the power of cycles, especially the 100,000-year cycle that shaped our planet for so long. It's a dance of ice and life, a rhythm that dictated which creatures thrived and which struggled. But about 11,700 years ago, something shifted. The familiar pattern faltered, and the giants of the Ice Age, the megafauna, began to disappear. Why did the cycle that sustained them for so long suddenly fail? Was it the speed of the warming, or the growing influence of humans, or perhaps a combination of both? It's a question that keeps me digging. Let's journey back to the last glacial maximum, about 20,000 years ago. Imagine ice sheets blanketing Canada, reaching into the northern United States, some places with ice up to 3 kilometers thick. That's like stacking the Burj Khalifa, the world's tallest building, 3 times over, but made of solid ice. The weight was so immense, it actually deformed the Earth's crust. Europe, too, was covered by the Fennoscandian ice sheet, blanketing Scandinavia, the Baltic, parts of Britain, and northern Russia. All told, we're talking about maybe 15 million cubic kilometers of ice sitting on land. If you were to spread all that ice evenly across the Earth, it would be 100 meters deep everywhere. With so much water locked up as ice, sea levels plummeted, not by a few meters, but by 120. Coastlines shifted dramatically. The English Channel vanished, and Britain became connected to mainland Europe. Indonesia transformed from a scattered archipelago into a single landmass connected to Asia. Australia, New Guinea, and Tasmania merged into one giant continent. And between Alaska and Siberia, a vast grassy plain called Beringia emerged where the Bering Strait now lies. The world map was utterly transformed, but it wasn't just the coastlines. The climate itself was drastically different. It was colder, yes, but also much drier. With so much water frozen and colder, ocean temperatures reducing evaporation, the atmosphere held less moisture. Deserts expanded and rainforests shrank. The Amazon basin was likely a mix of grassland and scattered trees, and the Sahara was even larger than it is today. Much of the world was covered in tundra or steppe, cold, dry grasslands with few trees. The ice sheets acted as massive refrigerators, generating cold, dense air that flowed off in powerful winds, carrying dust and silt for vast distances. In some parts of China, dust deposits accumulated to over 100 meters thick during these glacial periods. Imagine the dust storms, blotting out the sun for days. This was the world at peak glaciation, harsh, cold, dry, and windswept. And yet, life not only survived, but thrived. The megafauna weren't just scraping by. They dominated these ecosystems, perhaps exceeding the density of large animals in Africa today. The mammoth steppe was the dominant ecosystem across much of the northern hemisphere. This grassland, a unique mix of grasses, sedges, herbs, and low shrubs, adapted to the cold, supported enormous populations of large herbivores, mammoths, bison, horses, reindeer, all grazing together. It must have been an incredible sight. Mammoths were iconic, but they weren't alone. Woolly rhinoceroses, equally impressive, were similar in size to modern rhinos, but built for the cold, with thick woolly coats and massive horns used to clear snow. Like mammoths, We found them preserved in permafrost, revealing their adaptations to the extreme cold, like small ears and thick layers of fat. In the Americas, giant ground sloths reigned. Unlike their modern relatives, these were massive creatures. Megatherium americanum, the largest species, weighed over 3,800 kilograms, heavier than most elephants. They could stand on their hind legs, reaching heights of 4 meters or more, feeding on vegetation. And what's truly fascinating is that we found their burrows, actual tunnels, dug into hillsides, some 40 meters long and nearly 2 meters wide. Imagine encountering a multi-ton sloth emerging from an underground tunnel. It sounds made up, doesn't it? Yet, it's real. The floors and ceilings of some of these burrows even bear claw marks that match ground sloth claws perfectly. Scientists believe they dug these burrows either to escape temperature extremes or perhaps to hide from predators. Then there were the glyptodons, another bizarre group. They were relatives of modern armadillos, but scaled up to a ridiculous size. Some weighed up to 2 tons and walked on elephant-sized legs. Their bodies were protected by shells made of hundreds of bony plates fused together, a bit like a turtle, but much larger and heavier. These shells could be over 1.5 meters long, tough enough to stop almost any predator. Some glyptodon species even had tails covered in bony rings with spikes on the end, basically a medieval mace attached to their body. Recent biomechanical studies suggest they could rear up on their hind legs, meaning these armored tanks could stand upright and swing their spiked tails as weapons. Absolutely wild. The diversity of megafauna during the Ice Age is staggering. In North America alone, you had mammoths, mastodons, a different family of proboscideans with different tooth structures, American horses, American camels, giant beavers the size of bears, stag moose with enormous antlers, and multiple species of giant ground sloths. In South America, you had even more ground sloth species: glyptodons, giant armadillos, toxodons, kind of like hippo-sized rodent relatives, and macrochenia, which looked like a weird cross between a camel and a small elephant with a trunk. In Eurasia, there were mammoths, woolly rhinos, cave bears, steppe bison, giant deer called megaloceros, with antlers spanning over 3 and 1 or 2 meters, and more. And then there were the predators, because wherever you have large herbivores, you have large carnivores hunting them. Saber-toothed cats are probably the most famous Ice Age predator. Smilodon in the Americas had those incredible canine teeth, up to 18 centimeters long and flattened like blades. These weren't for crushing bone or gripping, but precision killing tools. Saber-tooths would use their powerful forelimbs to wrestle prey to the ground, then deliver a killing bite to the throat or belly, severing major blood vessels and causing rapid death from blood loss. The La Brea tar pits in California have preserved thousands of Ice Age animal bones, and saber-tooths are among the most common carnivores found there. This tells us they were successful predators, probably living in social groups like modern lions. And their prey wasn't small. They were taking down bison, young mammoths, horses, giant ground sloths, big, dangerous animals. Cave lions in Europe and Asia were larger than modern African lions and probably hunted similar prey. Cave bears, despite the scary name, were mostly herbivorous, but they were huge, up to half a ton, and their size alone made them formidable. And then there were giant short-faced bears in North America, which might have been the largest mammalian land predators ever to exist. These bears stood over 3 meters tall on their hind legs and may have weighed up to 800 kilos. There's debate about whether they were active predators or scavengers, but either way, you definitely didn't want to run into one. Dire wolves were another major predator, especially in the Americas. Real dire wolves, not the fantasy version. They were larger and more heavily built than modern gray wolves, with more powerful jaws designed for crushing bone. They hunted in packs and could take down prey much larger than themselves through coordinated attacks. The La Brea tar pits have yielded thousands of dire wolf fossils, more than any other carnivore, which suggests they were incredibly common. Even birds got in on the megafauna action. Teratorns were some of the largest flying birds ever, with wingspans over 3 and 1 to 2 meters. They probably soared on thermals like modern condors, searching for carrion. And there were even larger flightless birds in some regions. The Ice Age world had no shortage of impressive and terrifying predators. But here's what's really fascinating. All of these animals, from the smallest ground squirrels to the largest mammoths, were part of functioning ecosystems. They weren't just wandering around randomly. They had complex relationships with each other and with their environment. Herbivores competed for food and space. Predators hunted herbivores. Scavengers cleaned up the remains. Plants evolved to withstand grazing prey. It was all interconnected, and the megafauna themselves were ecosystem engineers. Mammoths, for example, didn't just eat grass. They knocked down trees, creating and maintaining open grasslands. They distributed nutrients across the landscape through their dung. They created trails and wallows. Their actions shaped the entire ecosystem. When you have animals that weigh several tons moving through an environment, they have a huge impact. Scientists have reconstructed these ancient ecosystems using multiple lines of evidence. Fossil assemblages tell us which animals lived together in the same places. Isotope analysis of bones and teeth tells us what they ate and what the climate was like. Ancient DNA can be extracted from permafrost sediments, even from sediments with no visible fossils. And this tells us which species were present. Cave paintings created by humans show what animals looked like and how they behaved. By combining all this evidence, we can paint a pretty detailed picture of Ice Age life. One thing that's become clear is that these ecosystems weren't static. They changed and shifted as the climate fluctuated. Remember, even within a glacial period, there were shorter-term climate variations. Events called Dansgaard-Oeschger oscillations caused rapid warming spikes lasting decades to centuries, then rapid cooling again. The Ice Age wasn't just one long frozen moment. It was a dynamic period, with temperature swings that dramatically changed the landscape. These shifts dictated where animals could live, what vegetation could grow, and ultimately, which species thrived and which struggled. It's a world that feels impossibly distant now. Our own ancestors were part of this world. They lived alongside these megafauna, hunted them, competed with predators, and adapted their technology and culture to survive in glacial conditions. In Europe, Neanderthals had already weathered these cycles for hundreds of thousands of years. They were remarkably cold adapted, with stocky builds and large nasal cavities to warm the air they breathed. They were skilled hunters, crafting complex weapons, mastering fire, and even expressing themselves through art and burial rituals. Then, around 45,000 years ago, modern humans, Homo sapiens, arrived in Europe, bringing new technologies, more complex social structures, and wider trade networks. We overlapped with Neanderthals for thousands of years, sharing the landscape and the same megafauna. In fact, genetic evidence reveals that we even interbred. Most people of European or Asian descent carry a small percentage of Neanderthal DNA, a tangible link to that ancient world. In other parts of the world, modern humans were also adapting to Ice Age conditions, coexisting with megafauna in Asia, Australia, which humans reached at least 65,000 years ago, and eventually the Americas. The interactions between humans and megafauna are intensely debated in Ice Age research, a topic we'll explore later. But for now, I think it's worth pausing to appreciate the sheer diversity and strangeness of life during peak glaciation. Imagine standing at the last glacial maximum, looking out over a landscape of ice sheets and cold grasslands with mammoths, rhinos, and giant sloths moving through it. It's a scene that will probably never exist again. These ecosystems are gone now. The megafauna are extinct. The mammoth steppe has vanished, replaced by forests and tundra. It's a lost world, shaped by the 100,000-year cycle. The cold phases of the cycle created the conditions, and life adapted to fill every available niche. For hundreds of thousands of years, this pattern repeated itself. Cold phase, megafauna thrive. Warm phase, forests expand. Cold phase again, megafauna return. It was a rhythm that life on Earth had adapted to. Then, about 19,000 years ago, something started to shift. The orbital cycles were moving into a configuration that favored warming. Northern hemisphere summers were getting stronger. The ice sheets began to melt. And what happened next would change everything. The transition from the last glacial period to our current interglacial was one of the most dramatic climate changes in recent Earth history. And caught in the middle of that transition were all these megafauna that had evolved to thrive in a frozen world. Most of them wouldn't make it through. So, we've touched on what these Ice Age giants look like, but let's delve into the details of how they actually lived. The more we learn about these animals, the more incredible they become, and some of the discoveries are genuinely surprising. Let's start with something that sounds almost impossible. Giant ground sloths digging massive burrows. When scientists first found these tunnels in South America, particularly in Argentina near Mar del Plata, they were initially of their origin. The burrows were huge, some reaching 5 to 6 meters below the surface, up to 1.8 meters wide and 40 meters long. That's the equivalent of a 2-story house worth of tunnel underground. Multiple mammal species were considered as possible diggers, but the evidence kept pointing to ground sloths, specifically species like Glossotherium and Celidotherium. The first clue was their arm bones. Ground sloth forelimbs were designed with a shovel-like structure, featuring unusually long second and third fingers, perfect for digging. And the bones were incredibly strong, designed to withstand the bending forces you'd encounter digging through hard soil, similar to the stresses that galloping mammals put on their leg bones. The second clue was their center of gravity. Paleontologists estimated from the skeleton that ground sloths had their center of gravity above their hind feet, which meant they could rear up into a bipedal posture. This is crucial for digging because your arms need to be free to excavate, not supporting your body weight. You can't dig effectively if you're on all fours. And the final smoking gun. Claw marks on the walls and ceilings of the burrows, perfectly preserved in the fossilized tunnels. Scientists matched these marks to ground sloth hand skeletons, and they fit exactly. These sloths weren't just big, they were engineering huge underground structures, despite weighing 800 to 4,200 kilograms. This is incredible behavior. Why were they doing it? The leading theories are either temperature regulation or predator avoidance. Underground, temperatures are much more stable than on the surface. If you're trying to escape extreme heat or cold, a burrow makes perfect sense. Or maybe they were hiding from predators like saber-toothed cats or giant short-faced bears. When you're big but not fast, going underground where predators can't easily follow you is a smart strategy. Either way, it shows these animals were far more behaviorally complex than we might expect from something called a giant sloth. Here's another fascinating discovery about ground sloths. In Ecuador, at a site called Tanque Loma, paleontologists found the remains of at least 22 Eremotherium sloths of various ages, all in the same location. They likely died during a drought, getting trapped in a shrinking watering hole. But the cool part is what this tells us about their behavior. They were congregating at watering holes, which means they were social animals living in groups. And they were probably wallowing in the water to escape heat and insects, similar to how hippos and rhinos behave today. Wait, imagine finding an animal's last meal perfectly preserved. That's what we've discovered with mammoths frozen in Siberian permafrost. Inside their stomachs, grasses, sedges, herbs, flowers, mosses, a snapshot of the mammoth steppe ecosystem. It's like stepping back in time, plant by plant. But it gets even better because we didn't just find their last meal. We extracted DNA from these frozen mammoths. We sequenced entire mammoth genomes. The genetic analysis revealed incredible adaptations to the cold. Mammoths, it turns out, had unique versions of hemoglobin. This protein carries oxygen in the blood, and theirs functioned better at freezing temperatures. Normal hemoglobin doesn't release oxygen efficiently when it's cold, a major problem for an animal in those conditions. But mammoth hemoglobin had mutations that compensated, allowing their blood to deliver oxygen effectively, even when their tissues were ice cold. We also found that mammoths had genes for small ears, sparse sweat glands, and improved fat storage, all coded into their DNA. Evolution didn't just change how they looked, it rewired their physiology at the genetic level. And here's a fact that I find particularly poignant. The last mammoths lived on Wrangel Island in the Arctic Ocean. Sea levels rose after the ice sheets melted, cutting the island off from the mainland. A population of only 500 to 1,000 mammoths survived there in isolation until about 4,000 years ago. That's after the pyramids of Giza were built. During the Bronze Age, mammoths and ancient civilizations overlapped in time. The last of these giants were walking around on a remote Arctic island, while humans in Egypt were building monuments and developing writing. Then they went extinct, likely due to inbreeding, habitat degradation on their small island, and perhaps climate change or the arrival of humans. The end of an evolutionary line that lasted for millions of years. The Ice Age wasn't uniformly frozen across the entire planet. Even during glacial periods, tropical and subtropical regions had warm seasons. The climate was cooler and drier than today, but equatorial regions weren't under ice sheets. Animals living in these areas still needed to deal with heat during the warmest parts of the year. Ground sloths in South America, for example, use the same strategies as large African mammals do today. Woolly rhinoceroses are another species we know a lot about from frozen specimens. Like mammoths, they had thick, woolly coats and were built for the cold. Their behavior, however, was probably different. Scientists think woolly rhinos were more selective feeders than mammoths. Mammoths were bulk grazers, eating whatever vegetation was available, while woolly rhinos seemed pickier, using their horns to dig through snow for specific plants. The giant deer, Megaloceros, had antlers that were absolutely insane. The largest specimens had antlers spanning over 3 to 1 to 2 meters from tip to tip, wider than a car. These antlers could weigh up to 40 kilograms. All that weight on your head takes serious neck and shoulder muscles. Scientists believe these massive antlers were primarily for display and competition between males, similar to how modern deer use their antlers. Cave bears are interesting because, despite their name and size, they were mostly herbivorous. Isotope analysis of their bones shows they ate primarily plants. Built like grizzly bears, they acted more like giant pandas. They hibernated in caves during winter, which is where we find most of their fossils. Some caves in Europe have thousands of cave bear bones, representing hundreds or thousands of individuals that hibernated there over millennia. Cave bears went extinct earlier than many other megafauna, around 27,000 to 24,000 years ago, well before the end of the last glacial period. The reasons aren't entirely clear, but it might have been related to competition with humans for cave space, climate changes affecting their food supply, or a combination of factors. Gryptodons are still blowing my mind the more I learn about them. Recent studies of their skeletal structure and muscle attachment points suggest they were capable of some surprising behaviors. They might have been able to rear up, but they also show adaptations for powerful digging, similar to modern armadillos, but scaled up massively. These armored giants might have dug burrows like their ground sloth contemporaries. Imagine tunnels big enough for a Volkswagen Beetle to drive through, created by armored animals with spiky tails. The Ice Age was wild. The predators of the Ice Age were just as specialized as the herbivores. Saber-toothed cats didn't just have those impressive fangs for show. Biomechanical studies of their skulls show they had relatively weak bite forces compared to modern big cats, but their neck muscles were incredibly powerful. Their hunting strategy was probably to use their strong forelimbs to wrestle prey down, then use their neck muscles to drive those saber teeth deep into the prey's throat or belly with precision. It wasn't about crushing force, it was about precision. Imagine a wolf with broken teeth or a fractured leg. It couldn't hunt alone, not effectively. But fossil evidence suggests that dire wolves lived in complex social structures, much like modern wolves. They cared for injured or elderly members, sharing food so that all could survive. That image stayed with me for days when I first read it. Giant short-faced bears, on the other hand, remained something of a mystery. Were they predators? Scavengers? The evidence is mixed, you see. Their long legs suggest they could cover great distances efficiently, useful for scavenging, but their powerful jaws and teeth? Definitely capable of killing prey. Perhaps they were opportunistic, hunting when they could, scavenging when necessary. And their sheer size, potentially the largest mammalian land predator ever, suggests they could intimidate smaller predators, stealing their kills. I picture a pack of dire wolves bringing down a bison only to have a giant short-faced bear show up, chasing them off to claim the carcass. One of the coolest things about Ice Age ecosystems is the source of our evidence, ancient DNA in sediments. Even without bones or visible fossils, DNA from animals can be preserved in frozen soil. Scientists have developed techniques to extract and identify this environmental DNA, revealing which species were present in different places at different times. It's filled in gaps in the fossil record, showing us that Ice Age ecosystems were even more diverse than we realized. For example, we now know that horses were present in areas where we don't have horse fossils, because we found horse DNA in the soil. And we've identified plants that grew in certain regions by finding their pollen and DNA. We can even tell what the climate was like by looking at which species of plants and insects were present. It's like reading an ancient ecological record written in genetic code. Humans, of course, were observing and interacting with all of this megafauna, and they left records of what they saw. Cave art from sites like Lascaux in France and Chauvet Cave show remarkably accurate depictions of Ice Age animals. The artists painted mammoths, woolly rhinos, bison, horses, cave lions, and more. These paintings aren't crude stick figures. They're sophisticated artworks, showing animals in motion, using the natural contours of the cave walls to create three-dimensional effects. The artists clearly spent a lot of time observing these animals to capture them so accurately. Some cave paintings even show details like fur patterns, seasonal coat changes, and behavioral poses. There's a famous painting of a woolly rhino that clearly shows its thick fur and the way it held its head. There are paintings of mammoths that show their characteristic domed heads and long tusks. These artworks are our direct visual record of what Ice Age megafauna looked like, created by people who saw them alive. Humans also left behind butchered animal bones, showing clear-cut marks from stone tools, mammoth bones with spear points embedded in them, campsites with hearths surrounded by the remains of horses, bison, and reindeer. The archaeological record proves that humans hunted megafauna and relied on them for food, materials for tools and clothing, and fat for fuel. Mammoth ivory was carved into art objects and tools. Hides were used for clothing and shelter. Bones were used to build dwelling structures in areas with scarce wood. Every part of these animals was utilized. But humans weren't just passive observers or simple hunters. There's evidence that humans might have used fire to manage landscapes, creating and maintaining the open grasslands that megafauna depended on. By burning vegetation regularly, humans could prevent forests from encroaching on grasslands, keeping habitats open for the large herbivores they hunted. This kind of ecosystem engineering might have actually helped support megafauna populations in some regions. The relationship between humans and megafauna was complex, not just predator and prey. The 100,000-year cycle had created this entire world. The cold phase of the cycle produced these unique ecosystems and drove the evolution of specialized megafauna adapted to frozen conditions. For hundreds of thousands of years, the pattern repeated. Ice sheets advanced, megafauna thrived. Ice sheets retreated, forests expanded. Ice sheets advanced again. Life adapted to this rhythm. But then, about 19,000 years ago, the cycle began shifting toward warming again. And this time, something was different. This time, humans had spread across most of the world, developed sophisticated hunting technologies, and existed in larger numbers than ever before. This time, when the climate started changing and the ice began to melt, the megafauna wouldn't just adapt and wait for the cycle to swing back to cold like they had for hundreds of thousands of years. This time, most of them were going to disappear forever. And we're still debating exactly why. So, around 19,000 years ago, the 100,000-year cycle reached a turning point. The orbital configuration shifted into a pattern that favored warming. Northern Hemisphere summers started getting stronger, receiving more solar radiation, and when that happens, winter snow starts melting more completely each summer. Ice sheets stop growing and begin their long retreat. The transition from glacial to interglacial conditions was underway. But the thing about deglaciation is that it's not smooth. It happens in fits and starts, with sudden collapses and temporary reversals. There are periods of rapid change that would have been noticeable within a single human lifetime. And this messiness, this is what makes understanding the extinction of the megafauna so complicated. The first major pulse of melting kicked off around 19,000 years ago and continued for several millennia. Sea levels began to rise as ice sheets melted, pouring water back into the oceans. During one period, meltwater pulse 1A, around 14 to 600 years ago, sea levels rose by roughly 20 meters in less than 500 years. 20 meters might not sound huge, but think about what that means. That's enough to flood vast coastal areas, submerge land bridges, and completely transform coastlines. All that water had to come from somewhere, and it came from collapsing sections of the great ice sheets. The Laurentide ice sheet, that massive dome of ice covering Canada, began breaking apart. The Fennoscandian ice sheet in Europe did the same. As they melted, they left behind a landscape that had been compressed under kilometers of ice for thousands of years. The land was scraped clean, covered in glacial till, and dotted with lakes formed in depressions carved by ice. It must have been a raw, bare landscape at first, slowly being colonized by plants as the climate warmed. But the warming wasn't steady. There were dramatic interruptions, the most famous being the Younger Dryas event. Around 14,700 years ago, the world had been warming for thousands of years. Ice sheets were in retreat. Things seemed to be heading toward interglacial conditions. Then suddenly, temperatures crashed. In Greenland, temperatures dropped by about 15 degrees Celsius in just a few decades, maybe even faster. Some evidence suggests it could have happened in as little as 10 to 20 years. The North Atlantic region was plunged back into near-glacial conditions that lasted over 1,000 years. The leading theory involves a catastrophic flood. As the Laurentide ice sheet melted, water pooled up behind it, forming enormous glacial lakes. The largest was Glacial Lake Agassiz, which was bigger than all of the modern Great Lakes combined. This lake was dammed in by the ice sheet itself, and when that ice dam failed, and geological evidence suggests it did multiple times, absolutely stupendous amounts of fresh water flooded into the ocean in a geologically instant time frame. We're talking about enough water to raise global sea levels by several meters, all released in months to years. This massive freshwater dump disrupted ocean circulation in the North Atlantic. There's this ocean circulation pattern called the Atlantic Meridional Overturning Circulation, or AMOC. It's basically a conveyor belt where warm surface water flows north, cools down near Greenland, becomes dense and sinks, then flows south at depth. This circulation transports enormous amounts of heat from the tropics to the northern hemisphere. But fresh water is less dense than salt water. When you dump a huge amount of fresh water into the North Atlantic, it floats on top and prevents the normal sinking of cold, dense water. This can slow down or shut down the AMOC. And when the AMOC stops, the northern hemisphere stops receiving that massive heat transport from the tropics. Temperatures crash, and you're back to near glacial conditions. The Younger Dryas had effects far beyond the North Atlantic. Climate patterns shifted across the globe. Some regions got drier, others wetter. Temperatures changed, and this had huge impacts on ecosystems and the animals living in them. For megafauna that were already stressed by changing habitats as the climate warmed and forests expanded, the Younger Dryas cold snap might have provided a temporary reprieve, but it also added instability to an already unstable situation. It had major impacts on human societies, too. In the Middle East, this is right around the time agriculture first developed. Some scientists think the climate stress of the Younger Dryas might have pushed hunter-gatherer groups to start deliberately cultivating plants as a way to end food security when wild resources became unreliable. If that's true, then this climate event, triggered by the 100,000-year cycle transitioning from glacial to interglacial, literally changed the course of human history, setting us on the path to farming, settled civilizations, and everything that followed. But eventually, around 11,700 years ago, the Younger Dryas ended, and it ended just as abruptly as it started. Temperatures spiked upward again. In some regions, temperatures rose by 10 degrees Celsius or more in just a decade or two. That's mind-bogglingly fast for natural climate change. The AMOC kicked back into gear. Heat flooded northward again. Ice sheets resumed their collapse, and this time there was no going back. The transition to full interglacial conditions was complete. We call this the beginning of the Holocene, our current geological epoch, and it marks the end of the last glacial period. For the megafauna, this was catastrophic. They had evolved over hundreds of thousands of years to thrive in cold, open grassland environments. But as the Holocene began, those environments were disappearing. The mammoth steppe, that unique ecosystem of cold grasslands that had supported enormous populations of large herbivores, was transforming. Forests were expanding. Grasslands were shrinking. The climate was getting wetter and warmer. For animals adapted to cold and dry conditions, this was a crisis, and the extinctions came fast. In North America, most megafauna disappeared between about 13,000 and 11,000 years ago. Mammoths, mastodons, horses, camels, giant ground sloths, saber-toothed cats, dire wolves, giant short-faced bears, all gone within a few thousand years. That's 70 to 80% of large mammal species just vanished. It was called the Quaternary Extinction Event, and the devastation was immense. As I read about it, I imagined the world transformed, emptied of giants. Europe, too, saw similar losses, though the exact timing shifted depending on the species. Woolly mammoths vanished from most places, holding on only in isolated pockets, like Wrangler Island. Woolly rhinos disappeared entirely. Cave lions, giant deer, gone. The megafauna that had dominated Europe during the Ice Age were either gone or drastically reduced. South America suffered as well. Giant ground sloths, all the different species that had evolved there, extinct. Glyptodonts, gone. Native horses and camels, extinct. Toxodons, macrauchenia, giant armadillos, all gone. The extinction wave swept through the Americas like wildfire. Australia had already lost most of its megafauna earlier, between 50 and 40,000 years ago. Giant wombats, enormous kangaroos, massive flightless birds, a marsupial lion, all disappeared. The timing in Australia seems to coincide more with the arrival of humans than with the last deglaciation. This adds another layer to the puzzle. What truly caused these extinctions? That's the question that has been debated for decades, and honestly, it's still not completely settled. Two main ideas exist: the climate change hypothesis and the human hunting hypothesis. The truth, I suspect, is a combination of both, with their relative importance changing depending on the region and the species we're talking about. The climate change idea suggests that the rapid warming and transformation of ecosystems was simply too much for these animals to handle. Megafauna had evolved for cold, open habitats. When those habitats disappeared in just a few thousand years, they couldn't adapt quickly enough. As forests expanded and grassland shrank, megafauna populations became fragmented into smaller and smaller pockets of suitable habitat. Small, isolated populations are vulnerable to inbreeding, disease, and random environmental fluctuations. This creates an extinction vortex, where declining populations face multiple threats that compound each other, making recovery impossible. There's solid evidence for climate being a major factor. The extinctions happened during a period of incredibly rapid climate change. Species adapted to cold climates, like woolly mammoths and woolly rhinos, went extinct, while species adapted to forests or warmer climates generally survived. This pattern strongly suggests climate played a big role. Also, megafauna had survived previous deglaciations. The 100,000-year cycle means there were multiple transitions from glacial to interglacial conditions over the past few million years. If megafauna survived those, why not this one? That's where the human hunting idea gains traction. Modern humans had spread across most of the world by the end of the last ice age, and humans are incredibly effective hunters, especially with the technological innovations that developed during this period. Atlatls, spear throwers that dramatically extend range and power, sophisticated hunting strategies involving coordinated groups, and later, bows and arrows. Human populations were growing and spreading into new territories. Critically, many megafauna had little or no evolutionary experience with human hunters, when humans first arrived in the Americas or Australia. The local megafauna hadn't evolved fear responses to these two-legged predators. They were, in a sense, naive prey. Modern examples show this pattern. When humans first reached oceanic islands with no previous human presence, the native birds and mammals often showed no fear and were easily hunted to extinction within decades or centuries. The same might have happened with Ice Age megafauna. They simply didn't recognize humans as threats until it was too late. And here's the thing about hunting megafauna: you don't need to hunt intensively to drive them extinct. These animals have slow reproductive rates. A female mammoth might have a calf only every 5 years. Mammoths don't reach sexual maturity until they're teens. If you kill even a few individuals per year from a population, especially females of reproductive age, you can drive the population into decline. Mathematical models show that even very low-intensity hunting, killing just a few percent of the population per year, can drive large-bodied animals extinct over centuries or millennia. And we know humans hunted megafauna. We've found butchered mammoth bones at human sites, spear points embedded in mammoth ribs, kill sites where multiple animals were driven off cliffs or into traps, and then butchered, cave paintings showing hunting scenes. The evidence is undeniable that humans hunted these animals. The question is whether hunting alone could cause extinctions, or whether it was just the final straw for populations already struggling with climate change. The timing is really suspicious in many regions. In North America, the extinctions coincide almost exactly with the expansion of Clovis culture, a group of humans with particularly effective hunting technology. Clovis points, these distinctive spear points, are found at sites with butchered mammoth remains. Within a few thousand years of Clovis people spreading across North America, the megafauna were gone. That's awfully coincidental timing. A study of the Anzac child, the only known Clovis individual, provides some interesting evidence. This was an 18-month-old child buried about 12,700 years ago in Montana. Scientists analyzed isotopes from the bones to reconstruct the diet of the child's mother. They found that mammoth contributed around 40% of the maternal protein diet, similar to the diet of specialized mammoth predators, like scimitar cats. This suggests Clovis people were heavily targeting mammoths, possibly as specialized mammoth hunters. But we need to be careful not to overinterpret. The Anzac child is one individual. We can't say all Clovis people had the same diet or hunting focus. The disappearance of the Ice Age giants, it wasn't a simple story. It wasn't just about humans hunting mammoths into oblivion. The truth, as I've come to understand it, is far more complex. The extinction pattern itself was uneven. Some species vanished quickly, while others clung on. Mammoths, for example, held out on Wrangler Island until about 4,000 years ago, millennia after their mainland cousins were gone. I've spent years considering how small populations of early humans could have possibly hunted mammoths to extinction across an entire continent. It's a question that still echoes in my mind. And what about the cave bears, gone even before many others, or the dire wolves, disappearing while gray wolves survived, and the bison, heavily hunted yet enduring? The reasons why some species survived and others didn't, that's still a puzzle we're piecing together. But one thing seems increasingly clear to me. It was the combination of climate change and human impact that proved fatal. Climate change put immense stress on these megafauna populations, breaking up their habitats and making food scarce. And then human hunting prevented these already fragile populations from bouncing back. It was a perfect storm, one that most couldn't weather. I've often wondered about the unseen consequences, too. Humans, with their fires used to reshape the land, altered the very vegetation itself. And the loss of the megafauna had its own ripple effects. Creatures like mammoths, these giant herbivores, were like ecosystem engineers, keeping grasslands open. When they vanished, those grasslands turned to forests, making life even harder for any remaining megafauna. It's all interconnected, a cascade of consequences. The Earth had a rhythm, a 100,000-year cycle that had sustained the megafauna for ages. Cold phases where they thrived, warm phases where they retreated. But this time, when the cycle shifted towards warmth, there was something new. Humans. Humans with advanced hunting tools and ever-growing numbers. The combination of rapid climate change and human press was simply too much for these magnificent creatures. And in just a few thousand years, the Ice Age world of giants vanished. But the story doesn't end there. There were humans living through these cycles, multiple species of them, and their story is just as fascinating. We weren't alone during the Ice Age. The Neanderthals were already well established when our ancestors arrived, and I believe they deserve far more recognition than they often receive. They were the original Ice Age survivors. They evolved in Europe and parts of Asia hundreds of thousands of years ago, living through glacial cycles long before modern humans left Africa. They weren't some brutish dead end. They were intelligent, sophisticated humans, incredibly well adapted to glacial conditions. Their adaptations were, in a word, brilliant. Consider their bodies, short and stocky, with barrel chests and thick, heavy bones. An average male might have been only about 160 centimeters tall, but they were built like tanks. Muscular, with bones showing massive muscle attachment sites. This wasn't random. It was an adaptation to the cold. Shorter, stockier bodies have less surface area relative to their volume, meaning less heat loss. It's Bergmann's rule in action. The same principle that made Ice Age megafauna so large. In cold climates, compact bodies retain heat better, and their faces distinctive, with large noses and wide nasal passages. This wasn't for looks. Those big nasal cavities acted like built-in air conditioners, warming and humidifying the frigid, dry air before it reached the lungs. Breathing super cold air repeatedly can damage lung tissue, so this was crucial. It's the same adaptation we see in woolly mammoths with their enlarged sinuses. Different species, same solution. Convergent evolution at work. But physical adaptations are only part of the story. Neanderthals had a sophisticated culture and technology. They made complex stone tools using the Levallois technique, carefully preparing a core and then striking off flakes of predetermined shapes. This requires planning, mental visualization. You have to see the finished tool in your mind before you even start working the stone. They also made wooden spears, carefully shaped and balanced, with tips hardened by fire. Some of these spears, have been found preserved in German peat bogs, and they are beautifully crafted. And Neanderthals hunted big, dangerous game. We've found Neanderthal sites with bones of bison, reindeer, wild horses, even woolly rhinoceros and mammoth. These weren't scavenged carcasses. The bones show clear butchery marks made with stone tools, while the meat was fresh. Neanderthals were actively hunting animals that could easily kill them if the hunt went wrong. That requires coordination, communication, planning, and courage. They used fire extensively and effectively, not just for warmth and cooking, but for making complex adhesives. Archaeologists have found Neanderthal tools with birch bark tar used to attach stone points to wooden handles. Making birch bark tar requires heating birch bark in the absence of oxygen at specific temperatures. This is a multi-step process that requires technical knowledge and careful control. You can't just stumble into figuring this out. They understood the process and could replicate it reliably. Even more impressive, Neanderthals had symbolic culture. They made ornamental objects, pierced shells, and eagle talons that were apparently worn as jewelry. They used pigments, possibly for body painting or decorating objects or cave walls, and they buried their dead, sometimes with what appear to be grave goods or in deliberate postures. There's a famous burial at Shanidar Cave in Iraq that includes evidence that might suggest flowers were placed in the grave, though that's still debated. But I think it hints at something profound. The fact that Neanderthals intentionally buried their dead tells me so much. It speaks to a deep humanity, a contemplation of mortality that I find profoundly moving. It wasn't just about survival. They thought about death. They created rituals, and they even made art. In Spanish caves, abstract geometric patterns and hand stencils exist from a time when Neanderthals were the only ones there. To me, these are among the earliest known examples of cave art, pushing back the timeline of symbolic behavior itself. This wasn't just one isolated group. Similar markings across multiple sites suggest it was part of their broader culture. So why did they disappear? That question has kept me up at night more times than I can count. The last Neanderthals died out around 40,000 years ago, just as modern humans were spreading into Europe from Africa and the Middle East. The timing is unsettling. Did we outcompete them, absorb them through interbreeding, or something more sinister? The genetic evidence makes one thing clear. Neanderthals and modern humans interbred. If you're of European or Asian descent, you likely carry 1 to 2% Neanderthal DNA. It might not seem like much, but it proves our ancestors had children together, children who survived and had their own families. Some Neanderthal genes are still with us, influencing our immune function, skin, hair, and even our susceptibility to certain diseases. So, in a way, they didn't completely vanish. They were absorbed into our gene pool, but as a distinct population with their own culture and identity, they didn't survive. A major factor was probably demographics. Modern human populations seem to have been larger and more widespread. When two populations compete for the same resources, sheer numbers often win. Even if individual Neanderthals were as capable as individual modern humans, being outnumbered 10 to 1 would eventually lead to being swamped. Modern humans also seem to have some technological advantages. While Neanderthals made excellent tools, modern humans developed more diverse and specialized toolkits. They created fine bone needles for sewing fitted clothing, offering better insulation. They crafted fishing equipment like hooks and harpoons, expanding their food sources. They made more prolific art and ornaments, possibly indicating more complex social structures or better communication systems. And modern humans had wider trade networks. Materials found at modern human sites came from hundreds of kilometers away, showing they exchanged goods over large distances. Neanderthal trade networks were more localized. Trade isn't just about stuff. It's about information exchange and social connections. Wider networks mean more people sharing ideas and innovations, accelerating cultural evolution and adaptation. Some researchers suggest modern humans might have had slightly better language abilities, allowing for more complex planning and coordination. Or perhaps they had different social structures more effective at resource acquisition or raising children. These are subtle differences not obvious in archaeological remains, but over generations they could compound into significant advantages. Climate might have played a role too. The late Ice Age was incredibly unstable, with rapid swings between cold and warm. Perhaps Neanderthals, specialized for cold, stable conditions, struggled more with these fluctuations. Modern humans, coming from Africa, which had its own climate variability, might have been more adaptable. But this is speculative. What's clear is that by 40,000 years ago, Neanderthals were gone, and modern humans were the only human species left in Europe. And we were spreading everywhere, adapting to every environment Earth offered. By the end of the last glacial period, humans had reached every continent except Antarctica, surviving the 100,000-year cycle at its most extreme phase. Modern humans developed an impressive array of technologies during the late Ice Age. Projectile weapons were a game changer. Early humans used thrusting spears that required getting close to prey, dangerous when hunting mammoth. Then they invented the atlatl, a spear thrower that acts as a lever arm to dramatically increase throwing range and power. Suddenly, they could attack from tens of meters away, much safer. Later, probably between 20 and 30,000 years ago, in some regions, humans invented the bow and arrow. This was huge. Arrows are faster and more accurate than atlatl darts. You can carry more ammunition. You can hunt smaller, faster animals more effectively. The bow might be one of the most important technological innovations in human history. It fundamentally changed how humans could acquire food and defend themselves. Hunting strategies became more sophisticated, too. There's evidence of drive hunting, where groups herded animals toward cliffs or into constructed traps, sites with hundreds of bison or horses driven off cliffs and butchered. This requires serious coordination among large groups of people. You need scouts, drivers, people positioned at the cliff to finish off injured animals, butchers, all working together with precise timing. It's complex social behavior that requires communication and planning. Fishing also became important. Humans developed harpoons, fish hooks made from bone, and nets, opening up aquatic resources. I sometimes find myself wondering about the hands that crafted the cave paintings at Lascaux and Chauvet. They weren't crude drawings, not at all. They're sophisticated, dynamic images of animals rendered with incredible skill and accuracy. The artists even used the natural contours of the cave walls to create three-dimensional effects, mixing pigments to achieve different colors. During the Ice Age, humans relied heavily on fish, a major food source, especially in coastal and riverine areas. And fishing, I imagine, was relatively low risk compared to hunting mammoth. Coastal sites reveal just how much they depended on the sea, with enormous shell middens representing thousands upon thousands of meals. Clothing technology also improved dramatically. The bone needles that appeared around 40,000 years ago allowed for sewing-fitted clothing, with sleeves and clothes. I know from personal experience that simply wrapping animal hides around yourself isn't very effective at trapping body heat. Fitted clothing is far better. This seemingly simple technology probably allowed humans to survive in even colder regions and remain active during winter, rather than just hunkering down. Shelter evolved, too. In regions with scarce wood, people built structures using mammoth bones and tusks as frameworks covered with hides. These mammoth bone houses have been found in Ukraine and Russia. Some used bones from dozens of individual mammoths, representing thousands of kilograms of material. These were substantial dwellings, not temporary camps. People were investing serious effort into creating comfortable, long-term living spaces. Beyond mere survival, Ice Age humans created stunning artwork. It wasn't just cave paintings either. People carved figurines from ivory, bone, and stone. The Venus figurines, those stylized female forms found across Europe, date to this period. Some even have elaborate details like hairstyles or clothing carved into them. People made musical instruments, flutes carved from bird bones or mammoth ivory. They created elaborate burials with grave goods, including thousands of ivory beads sewn onto clothing. One burial of children at Sungir in Russia included so many beads that researchers estimated it would have taken thousands of hours to make them. These people valued symbolic expression enough to invest enormous time and effort into it. Why did humans create art? Probably lots of reasons. Some cave art might have been connected to hunting magic or spiritual rituals. Some figurines might have been religious or fertility symbols. Some art was probably just for aesthetic plea or social bonding. The point is, Ice Age humans weren't just focused on survival. They had rich inner lives, symbolic thinking, spiritual beliefs, and cultural traditions. They were fully modern mentally and behaviorally, even though they lived in conditions we'd find incredibly harsh. Human populations during the Ice Age weren't huge by modern standards. Estimates suggest maybe just a few million people worldwide, but those people had spread across most habitable regions. They'd reached Australia by at least 65,000 years ago, crossing significant water gaps, even during low sea levels. They'd spread throughout Asia and Europe, and critically, they'd made it to the Americas. The peopling of the Americas is fascinating. During peak glaciation, when sea levels were low, the Bering Land Bridge connected Asia and North America. But this wasn't just a narrow strip. Beringia was a vast region, probably thousands of kilometers wide, with its own ecosystems. And humans crossed it, probably following game animals, entering a continent with no previous human population and megafauna that had never encountered human hunters. The timing is still debated. The oldest widely accepted sites in the Americas date to about 15 to 16,000 years ago. But there are controversial sites that might be older, suggesting people could have arrived as early as 20 to 30,000 years ago. Either way, once humans were in the Americas, they spread incredibly fast. Within just a few thousand years, there's evidence of human presence from Alaska to the southern tip of South America. That's an incredible migration speed, and remember, the American megafauna went extinct shortly after humans arrived. Mammoths, mastodons, giant ground sloths, horses, camels, all gone within a few thousand years of human appearance. The timing suggests humans played a major role. The Clovis people, with their distinctive spear points and apparent focus on hunting mammoths, have been particularly implicated. But it's complicated. Climate was changing rapidly at the same time. It's probably both factors working together. By the time the Holocene began 11,700 years ago, humans were the dominant large animal on multiple continents. We'd outlasted Neanderthals and other human species. We'd survived the wild climate swings of deglaciation. We'd adapted to every environment from tropical rainforest to Arctic tundra. And we developed incredibly diverse cultures and technologies. Despite being one species genetically, humans showed cultural diversity that no other species has ever matched. This set the stage for what came next: the development of agriculture and the rise of civilization. But that's a different chapter in the story. The point is, the Ice Age and its 100,000-year cycle was the crucible that forged modern human behavior. The technological innovations, the social structures, the symbolic thinking all developed or were refined during the harsh conditions of glacial cycles. We are, in a very real sense, products of the Ice Age. Our success as a species was built on adaptations to a frozen world, and now that world is gone, melted away as the cycle shifted to its warm phase. The question is, I sometimes wonder if we're truly adapted to the world we inhabit now. Are we, in a sense, carrying evolutionary and cultural baggage from an ice age that ended millennia ago? The 100,000-year cycle has shifted, the ice has melted, and the megafauna are mostly gone. We now live in a world completely different from what our ancestors knew for hundreds of thousands of years. We call this the Holocene, our current interglacial period, and it's when everything changes for human societies. Around 11,700 years ago, the Younger Dryas cold snap finally ended. Temperatures rose rapidly, then stabilized into conditions similar to today. The climate became warmer and wetter than it had been during the glacial period. Forests expanded massively, spreading across what had been cold grasslands and tundra. Sea levels continued to rise as the last major ice sheets melted, flooding coastlines and creating the geography we recognize today. It was a dramatic and relatively fast transformation. For humans who'd been living as hunter-gatherers, this presented both opportunity and challenge. Warmer temperatures meant longer growing seasons, more diverse vegetation, and a more predictable climate. But the megafauna they had been hunting were disappearing. Those massive herds of mammoth, bison, and horses that had been reliable food sources were gone or going extinct. Humans had to adapt their subsistence strategies quickly or face serious problems. In some regions, people turned heavily to fishing and gathering shellfish. Coastal sites from this period show enormous shell middens and fishbone deposits. The ocean was stable and productive, providing reliable food. In other regions, people focused more on smaller game like deer, rabbits, and birds, supplemented with gathered nuts, seeds, roots, and berries. These required different hunting techniques than megafauna hunting. You can't drive deer off cliffs effectively. You need different tools, different strategies. But in a few special regions, something revolutionary happened. People started deliberately planting and cultivating wild plants. This was the beginning of agriculture, and it changed everything about human society. The first clear evidence of agriculture appears in the Fertile Crescent of the Middle East around 11 to 10,000 years ago. People started cultivating wheat and barley, domesticating sheep and goats. In China, rice and millet cultivation began around 9,000 years ago. In Mesoamerica, maize was domesticated around the same time, in multiple regions independently, within just a few thousand years of each other. Humans invented farming. Why did agriculture develop when it did? That's been debated forever. One theory is population pres. During the Ice Age, human populations were kept relatively small by harsh conditions and limited food resources. But as the Holocene began and conditions improved, populations might have grown to the point where hunting and gathering couldn't support everyone. Agriculture produces more calories per unit of land than hunting and gathering, so it can support higher population densities. If your population outgrows your hunting territory, you either starve, migrate, or innovate. Some groups chose innovation. Another theory emphasizes climate stability. Agriculture requires planning for the future. You plant seeds and wait months for harvest. This only makes sense if you can reasonably predict that conditions will remain suitable for plant growth. During the wildly fluctuating climate of the late Ice Age, with events like the Younger Dryas, that wasn't a safe bet. But during the Holocene, the climate became more stable and predictable. You could plant in spring and be reasonably confident summer would come and your crops would mature. This stability made agriculture viable in a way it hadn't been before. There's also a theory that the Younger Dryas specifically triggered agriculture in the Middle East. The idea is that hunter-gatherers in the Fertile Crescent had developed semi-sedentary lifestyles during the warm period before the Younger Dryas, living in villages and intensively harvesting wild grains. Then the Younger Dryas hit, and those wild grains became less productive. To maintain their lifestyles and avoid starvation, people started actively cultivating the grains, selecting for varieties that produced more food. When the Younger Dryas ended, they were already farming and just continued. Whatever triggered it, agriculture spread rapidly once it started, and it came with a massive package of changes to human society. You can't be nomadic and farm effectively. You need to stay in one place to tend crops and protect them from animals and thieves. So agriculture led to permanent settlements, villages that grew into towns and eventually cities. These settlements required new forms of social organization. Who controls the land? How do you store surplus food? How do you defend your settlement? How do you resolve disputes? Agriculture also changed human diets dramatically, and not always for the better. Hunter-gatherers typically had diverse diets with lots of protein and varied nutrients from many plant and animal sources. Early farmers ate mostly carbohydrates from a few grain crops, supplemented with whatever else they could grow or gather. Skeletons from early agricultural societies show signs of nutritional stress compared to hunter-gatherers. More cavities from all the starchy foods, shorter average stature, and diseases associated with dietary deficiencies. Agriculture allowed population growth, but individual health often declined. Disease became a much bigger problem once humans started living in permanent settlements. When you're nomadic and moving frequently, your waste gets left behind, and diseases don't have time to build up. But in permanent villages, the shift to agriculture wasn't just a step forward. It was a doorway to a whole new world of problems and possibilities. With dense populations came waste, contaminated water, and close contact with animals, perfect breeding grounds for infectious diseases. It's sobering to realize that many of the diseases that plague us today, like measles, smallpox, tuberculosis, and influenza, originated in domestic animals. They made the jump to us when we started living in close quarters with livestock. Farming, in a way, made us more vulnerable. Yet agriculture had an overwhelming advantage. It could support far more people per unit of land. A square kilometer of wheat fields can sustain dozens, even hundreds of people, while the same area of wild land might support only a handful of hunter-gatherers. This meant agricultural societies could grow much larger, and more people meant more workers, soldiers, inventors, more of everything. When agricultural societies encountered hunter-gatherer societies, the farmers usually won through sheer numbers, even if individual hunter-gatherers were healthier or better warriors. Over thousands of years, agriculture spread across most of the world where the climate allowed. Sometimes, this spread occurred through the migration of farming peoples, displacing or absorbing hunter-gatherers. Other times, hunter-gatherers adopted farming from their agricultural neighbors. Either way, most humans transitioned from mobile hunting and gathering to settled farming, setting the stage for the rise of complex civilizations. Permanent settlements grew into cities. Cities required food from surrounding agricultural areas, leading to the development of trade networks. Trade, in turn, required record-keeping, which led to the invention of writing in multiple regions independently. Complex societies developed hierarchies with rulers, priests, craftspeople, farmers, and slaves forming different social classes. Organized religion became more prominent, with monumental architecture like temples and pyramids built to honor gods or rulers. Specialized occupations emerged as some people focused full-time on pottery, metalworking, weaving, or administration instead of food production. The first civilizations arose in river valleys where agriculture was particularly productive. Mesopotamia between the Tigris and Euphrates, Egypt along the Nile, the Indus Valley in South Asia, the Yellow River in China. These civilizations developed writing, mathematics, astronomy, metallurgy, all the hallmarks of complex society. And all of this happened within just a few thousand years after the end of the last ice age. It's an incredibly rapid transformation, from small mobile hunter-gatherer bands to cities with tens of thousands of people. But here's something important to remember. While these civilizations were rising, there were still hunter-gatherer societies thriving in other parts of the world. Australia's Aboriginal peoples maintained their hunter-gatherer lifestyles for tens of thousands of years after agriculture was invented elsewhere. In the Americas, many groups remained hunter-gatherers, even as others developed agriculture and built cities. In Africa, groups like the San people hunted and gathered successfully until very recently, and some still do. Agriculture wasn't inevitable or universally adopted. It was one strategy among many, one that happened to be very successful at supporting large populations and complex societies, but not the only viable way to live. The ecological consequences of this Holocene transition were profound. It wasn't just about the extinction of megafauna. Forests expanded dramatically, changing countless ecosystems. Species adapted to open grasslands had to move, adapt, or go extinct. Cold-adapted species retreated northward or to higher elevations, while warm-adapted species expanded their ranges. The distribution of species across the planet shifted massively within just a few thousand years, and humans were increasingly shaping these ecosystems, often in ways we didn't fully appreciate until recently. Indigenous peoples around the world used fire as a landscape management tool, burning regularly to maintain open areas that attracted game animals or promoted the growth of useful plants. This burning had huge effects on vegetation patterns. It's quite humbling to realize that what we often think of as natural, pristine ecosystems are actually anthropogenic, shaped by thousands of years of human fire management. In Australia, Aboriginal burning transformed large areas from dense forest to open woodland and grassland. In North America, Native American burning maintained vast prairies and savannas that might otherwise have been forested. When Europeans arrived and disrupted these burning practices, ecosystems often shifted dramatically. Forests grew where they hadn't been for millennia. Fire-adapted species declined, while fire-sensitive species increased. The wilderness that Europeans saw wasn't untouched nature. It was often the result of thousands of years of active human management. The extinction of megafauna also had cascading ecological effects that we're still trying to fully understand. Mega-herbivores like mammoths weren't just eating plants. They were ecosystem engineers. They knocked down trees, maintained open areas, distributed nutrients through their dung, and created trails and wallows. When they disappeared, these functions disappeared too. Some scientists believe forests expanded after the Ice Age partly because there were no longer giant herbivores suppressing tree growth. There's even a hypothesis that megafauna extinction contributed to climate change. Large herbivores produce a lot of methane, a potent greenhouse gas, from their digestive systems. When megafauna populations crashed, methane emissions might have decreased significantly, and the transformation from open grasslands to forests changed the reflectivity of the land surface, affecting how much solar energy was absorbed versus reflected. The loss of those massive creatures, the megafauna, it affected us too. For thousands of years, humans had relied on them for survival. Their extinction wasn't just about losing a food source, it meant losing vital materials. I've read accounts of mammoth ivory being used for everything from tools to art, even construction. Hides provided clothing and shelter, and bones were crafted into needles and dwelling frameworks. Their disappearance forced us to find substitutes, and that likely spurred technological innovation. In a way, the megafauna extinction might have even sped up the transition to agriculture in some regions. If your primary food source vanishes and you can't replace it by hunting a smaller game, you either starve or find a new way to survive. Agriculture became that strategy. Those extinctions that ended the Ice Age world might have inadvertently pushed humans toward the lifestyles that would create modern civilization. The Holocene, the time since the last Ice Age, has been unusually stable compared to the climate swings of the Pleistocene. There have been variations, warm and cold periods, droughts and floods, but nothing like the dramatic shifts of the Ice Age, with its rapid warming and cooling events. This stability probably helped civilizations develop. It's hard to build cities and plan for agriculture when the climate might drastically change within a single generation. But Holocene stability allowed humans to make long-term plans and investments, building irrigation systems and monumental architecture that took decades or even centuries to complete. Different parts of the world experienced the Holocene differently. The Sahara Desert, now a vast, empty wasteland, was actually green and wet during the early Holocene. From about 11,000 to 5,000 years ago, increased monsoon activity brought more rain to North Africa. Rivers flowed through what's now desert. Lakes filled valleys. Vegetation covered areas that are now bare sand. People lived throughout the region, herding cattle and developing agriculture. I remember seeing rock art from this period, showing hippos, giraffes, and elephants, animals that now seem impossibly out of place. But then, around 5,000 years ago, the African monsoons weakened and the Sahara dried out relatively rapidly. Within just a few centuries, the Green Sahara became the desert we know today. This desertification forced populations to migrate, many moving to the Nile Valley where water remained available. Some historians believe this migration and concentration along the Nile contributed to the development of ancient Egyptian civilization. Climate change driving human migration, driving civilization development. It's all interconnected. Similar stories played out elsewhere. The Middle East was relatively wet in the early Holocene, supporting agriculture and early civilizations. But droughts have repeatedly stressed or collapsed civilizations there. In Mesoamerica, droughts have been linked to the collapse of Maya civilization. In the American Southwest, extended droughts force the abandonment of settlements like Mesa Verde. Climate variability during the Holocene has been a constant factor shaping human history, even though the swings were mild compared to the Ice Age. And here we are now, roughly 11,700 years into the current interglacial period. Based on past interglacials, we should eventually slide back into glacial conditions at some point. Different models give different predictions. Some suggest we have thousands of years before the next glaciation begins. Others think tens of thousands of years. The orbital cycles are complex, and their effects don't always line up predictably. But there's a massive wild card now. Human activity is affecting global climate on a scale that might override the natural cycles entirely. We've increased atmospheric carbon dioxide from the natural interglacial level of about 280 parts per million to over 420 parts per million. That's a 50% increase in just a couple of centuries. The ice core records going back 800,000 years show nothing like this. We're in completely uncharted territory. And this brings us to the big question, what happens next? So, here's where things get really interesting and honestly a bit scary. We've spent this whole time talking about how the 100,000-year cycle has controlled Earth's climate for millions of years, creating ice ages and shaping the evolution of life, including humans. But now, for the first time in the history of this cycle, one species has the power to override it, and that species is us. Some scientists think we've already delayed or canceled the next glaciation. The extra carbon dioxide we've pumped into the atmosphere, warming the planet, making it unlikely that northern hemisphere summers will be cool enough to allow ice sheet formation, even when the orbital cycles shift toward glacial conditions. We might have prevented the next ice age from ever happening. Sounds good, right? Nobody wants kilometers of ice covering Canada and Scandinavia again. But the problem is, we're not just preventing the next ice age. We're warming the planet way beyond normal interglacial conditions. And we're doing it incredibly fast. Let's talk about what we've learned from studying ice age cycles and why it matters right now. First, and most importantly, the climate system has tipping points. It's not linear or gradual. You can push the system for a while and see only small changes, then suddenly cross a threshold and boom, rapid dramatic shifts happen. The Younger Dryas is the perfect example. Gradual warming, then catastrophic freshwater flooding, then abrupt climate reversal within decades. The system flipped states faster than human lifetimes. We're seeing similar threshold behavior today in multiple parts of the climate. Ice sheets don't melt in a predictable way. I've learned they can remain stable for centuries, only to suddenly accelerate their melting when they hit a certain breaking point. It's not a smooth process at all. Small forces can trigger huge reactions. And right now, we're pushing several of these systems toward their tipping points all at once. Arctic sea ice is declining so dramatically. Since satellite measurements began in the 1970s, the minimum extent in summer has dropped by about 40%. Some models even suggest we could see ice-free Arctic summers within decades. And it's all connected through feedback loops. Ice reflects sunlight, but ocean water absorbs it. Less ice means more heat absorption, which leads to even more warming and ultimately even more ice loss. It's a self-reinforcing cycle. The Greenland ice sheet is losing a mass at an accelerating rate around 250 billion tons per year, according to recent measurements. It holds enough ice to raise global sea levels by about 7 meters if it were all to melt. Now, nobody expects that to happen all at once, but even losing a fraction of that over the coming centuries would have a massive impact on coastlines worldwide. And once major melting begins, these feedback effects make it incredibly difficult to stop. Darker, exposed rock absorbs more heat. Meltwater lubricates the base of the ice, causing it to flow faster. Warm ocean water gets underneath and melts it from below. All positive feedbacks, amplifying the initial change. The West Antarctic ice sheet is particularly concerning, mostly because a large part of it sits on bedrock below sea level. Warm ocean water is already making its way underneath, causing melting. Some scientists believe that major portions of it might be destined to collapse over the coming centuries, even if we were to stop warming today. If that happens, we're looking at a potential 3 to 5 meters of sea level rise. That would completely reshape coastlines across the globe and displace hundreds of millions of people. The carbon cycle is also being disrupted in ways that mirror the Ice Age cycles, but in reverse and at a much faster pace. During glacial periods, carbon dioxide levels dropped to around 180 to 200 parts per million. During interglacial periods, they rose to about 280 to 300 parts per million. This swing of roughly 100 parts per million took tens of thousands of years, driven by natural ocean and vegetation processes. But in just over a century, we've increased carbon dioxide by over 140 parts per million. We're replicating the entire natural cycle's range in a tiny fraction of the time, and we're blowing past natural interglacial levels, venturing into territory that the Earth hasn't seen for millions of years. The last time carbon dioxide levels were this high was probably during the Pliocene epoch, around 3 million years ago. Temperatures were several degrees warmer than they are today. Sea levels were 15 to 25 meters higher, and the Arctic was forested instead of covered in ice. That's where we're heading if we don't change course. The rate of change matters just as much as the magnitude. Ecosystems can adapt to gradual changes over thousands of years. Species migrate, evolution selects for new traits, and ecological communities reassemble. But when change happens in decades or centuries, there's simply no time for gradual adaptation. Species either move fast enough or they face extinction. We're already seeing shifts in the ranges of thousands of species. Plants are flowering earlier, animals are moving toward the poles or up mountains, and ocean species are shifting to cooler waters. Some species are adapting successfully, while others aren't, and we're likely headed for another extinction wave, maybe not as dramatic as the megafauna extinctions, but significant nonetheless. Current extinction rates are already elevated above background levels, and climate change is adding another major stressor on top of habitat loss and pollution. Here's something that often keeps scientists up at night. During Ice Age cycles, carbon dioxide changes were a feedback, not a forcing. Orbital variations changed sunlight distribution, which affected temperature. These temperature changes then affected ocean chemistry and vegetation, which in turn changed atmospheric carbon dioxide. Carbon dioxide amplified the temperature changes. It was a feedback loop within the system responding to external astronomical forcing. But what we're doing is different. We're directly forcing carbon dioxide changes by burning fossil fuels. This is direct forcing, not feedback. And all those natural feedbacks that amplified carbon dioxide changes during Ice Age cycles are still operating. They're amplifying the changes we're causing. We're pushing on a system with built-in amplifiers, and we don't fully understand all of them or where the thresholds lie. Permafrost is a huge wild card. There's around 1,500 billion tons of organic carbon stored in frozen Arctic soils. That's roughly twice as much carbon as is currently in the atmosphere. As the Arctic warms, permafrost thaws, and microbes start decomposing that organic matter, releasing carbon dioxide and methane. It's a classic feedback loop. Warming causes thawing, thawing releases greenhouse gases, and greenhouse gases cause more warming. How fast this happens is uncertain, but the potential for permafrost to become a major additional carbon source is real and quite frightening. The ocean has absorbed about 90% of the extra heat trapped by greenhouse gases so far, which has slowed atmospheric warming, but at the cost of warming the ocean itself. Warm water holds less dissolved oxygen. And we're already seeing expanding dead zones where oxygen levels have dropped too low to support most life. Marine organisms are stressed by warming, acidification from dissolved carbon dioxide, and oxygen loss all at the same time. Coral reefs are being devastated by repeated bleaching events. These ecosystems, which support enormous biodiversity, are collapsing. The climate is complicated, even counterintuitive. I find myself pondering what to do with this knowledge, this understanding of the 100,000-year cycle. It teaches us that Earth's climate is incredibly sensitive to even relatively small changes. The orbital variations that trigger ice ages, tiny changes in seasonal sunlight, yet enough to tip the whole system when combined with feedback loops. Now, we're applying a forcing much larger and faster than those orbital variations. The response, it will be substantial. The only real question is how substantial and on what timescale. We also learned that climate has momentum. Ice sheets take millennia to grow, yet they can collapse much faster. Once major melting begins, stopping it becomes incredibly difficult. Ocean circulation changes can be hard to reverse. Some of the changes we're causing are essentially irreversible on a human timescale. Even if all emissions stopped tomorrow, temperatures would remain elevated for centuries as the ocean and atmosphere slowly find their equilibrium. Sea level would continue rising for centuries, even millennia, as ice sheets respond to the warming already set in motion. It's uncomfortable to contemplate, isn't it? We've probably already committed to significant changes, even with aggressive emission reductions. Some warming, some sea level rise, some ecosystem disruption is essentially baked in. The real question now is, how much more will we add? Every bit of additional warming makes things worse. Every tenth of a degree matters when dealing with systems teetering on tipping points. The paleoclimate record is clear. Rapid climate change is incredibly hard on societies. The changes at the end of the Ice Age contributed to megafauna extinctions and forced major shifts in human life. Droughts throughout the Holocene toppled civilizations, and those were natural variations, changes over which societies had no control. We're causing changes faster and potentially larger than those natural variations. With over 8 billion people to feed and house, many in areas vulnerable to climate change, the implications are staggering. Coastal cities face flooding from rising seas. Agricultural regions face shifting rainfall and more extreme weather. Water resources are stressed by changing precipitation and glacial melt. Tropical regions could see temperatures exceeding human survivability thresholds for outdoor work during heat waves. Island nations could literally disappear. The humanitarian implications are enormous and unequally distributed. Those who contributed least to causing climate change are often the most vulnerable to its effects. But understanding the problem is, at least, the first step toward addressing it. We know more about climate now than ever before. We can see changes happening in real time with satellites and monitoring. We can model future scenarios with increasing accuracy. And we have technologies available that could dramatically reduce emissions if deployed at scale. Solar and wind are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. Energy storage is improving. Carbon capture is being developed. though not yet proven at the necessary scale. The challenge isn't really technological anymore. It's political, economic, and social. Getting 8 billion people to coordinate on emission reductions, equitably distributing costs and benefits, navigating competing interests, that's the hard part. Climate change is the ultimate tragedy of the commons. Individual actors benefit from burning fossil fuels, but everyone suffers the consequences. Solving it requires collective action at a scale humanity has never achieved. Some people feel despair. The problem seems too big, changes too slow, obstacles too numerous. I understand that feeling, but humans have navigated existential challenges before. We survived the Ice Age through adaptation and innovation. We transitioned from hunting megafauna to agriculture, fundamentally transforming our relationship with the planet. We've overcome diseases, expanded lifespans, created technologies that would seem like magic to our ancestors. We're not helpless. We're just facing a problem requiring unprecedented coordination. The 100,000-year cycle will eventually resume, assuming we don't permanently alter it. The orbital mechanics haven't changed. Naturally, Earth would eventually slide back into glacial conditions tens of thousands of years from now. But we're writing a new chapter, one where human activity is a major climate driver, not just a responder. We're affecting the planet on a scale comparable to the astronomical forces that controlled climate for millions of years. No species has ever had this influence. It's both inspiring and terrifying. Future geologists studying sediments millions of years from now will see a clear marker. They'll see isotope ratios reflecting massive carbon combustion, extinction signatures, novel materials like plastics and concrete in the sediment. They'll recognize something unprecedented happened during this brief moment. Whether they'll also see evidence that we successfully navigated the crisis, that's still open. The answer depends on what we do in the coming decades. The cycle reminds us that climate is dynamic, sensitive to forcing, full of feedbacks and tipping points. It's not a stable, unchanging background. It's an active system responding to inputs. For millions of years, those inputs were natural. Now, we're adding a new input, and the system is responding. The question isn't whether it will respond, but how. We are living through a truly unique moment. In all of Earth's 4.5 billion years, never before has a single species understood the global climate system while simultaneously altering it. That's us. We possess knowledge and power no organism has ever had. What we do with that power now will determine Earth's trajectory for thousands, even millions of years. No press, as they say. The Ice Age cycles have shown us that life is resilient. Earth has been through dramatic climate changes, and life has always survived, adapted, thrived. It survived the asteroid that killed the dinosaurs. It survived ice ages. It will survive this too. The real question is whether human civilization as we know it will thrive, or whether we'll face massive disruptions that could have been avoided with foresight and decisive action. I started by talking about the mystery of the 100,000-year cycle and how scientists solved it through patient work. That same scientific community is now warning us about anthropogenic climate change, using the very same methods that revealed the Ice Age cycles to begin with. If we trust the science that explained the past, shouldn't we trust it when it predicts the future? It's pretty clear we're pushing the system hard, and we will see significant responses. The window for avoiding the worst outcomes is closing rapidly. The Ice Age taught our ancestors to be adaptable and innovative. That's in our DNA, I believe. We can use those traits to navigate the challenge we've created, but we need to act collectively and quickly. The climate system has momentum and inherent time lags. Actions taken today won't show their full effects for decades, but inaction today commits us to changes that will unfold for centuries. Every year of delay only makes the eventual response harder and more disruptive. So, where does that leave us? We're 11,700 years into an interglacial period that should eventually end. We are armed with an understanding of how climate works, and we are actively changing it faster than natural processes typically do. The 100,000-year cycle that shaped human evolution is now being overridden by human activity. We've become a geological force, undeniably. The only question that remains is whether we will use that power wisely or recklessly. The answer will determine what kind of planet future generations inherit, and whether they'll view us as ancestors who rose to the challenge or as a cautionary tale of a species that understood the problem but ultimately failed to act. The clock is ticking relentlessly. The cycle that sustained life for millions of years is still operating in the background. But for the first time, it might not even matter. For the first time, one of the species it created has the power to override it entirely. What we do with that power in the next few decades will determine not just our future, but the future of countless other species sharing this planet with us. The Ice Age is over. The question now is, what comes next? And unlike our ancestors, who simply had to survive the cycle, we have the power to shape it. That's both an incredible responsibility and an incredible opportunity. It's time to see what we do with it.